All right, thank you. Hi, everyone. So I'll be presenting the paper, Deep Hierarchical Approach to Lifelong Learning in Minecraft. So just a brief outline of my presentation. So first I'll give an introduction of what lifelong learning is, and then some of its challenges, and then I'll introduce the game Minecraft, and then provide some background information. Then I'll introduce the model that proposed by the author, which is called the Hierarchical Deep Reinforcement Learning Network, or the HDRLN. And then I'll talk about their experiments that they did in the Minecraft, and then the result, conclusion, contribution, and future work. So lifelong learning, by definition, lifelong learning is the continual learning of tasks from one or more domain over the course of a lifetime using a lifelong learning system. And then there are three basic building blocks of a lifelong learning system. The first is the ability of retaining knowledge that was learned from before, and also it must be able to select the knowledge learned from before and know when to reuse those knowledge and apply them into a new task. And the third one is the system approach that ensures a efficient interaction between the two. And then it keeps on applying to the new tasks. So what are the challenges of lifelong learning approach? So the first is the dimension. So once the state and action space increases, it becomes more harder and harder to model and solve new tasks, and also planning over a potential infinite time horizon, and how to efficiently retain and reuse the knowledge learned from before is also difficult. And what's interesting is that all these challenges were incorporated into the single game Minecraft, which itself is a open research problem in high-dimensional lifelong learning. So I'm pretty sure many of you have either played or heard the game Minecraft. I never played this, but it's an amazing game. It's great. It's the second best-selling games in the history. The only one that better was Tetris, and it was bought by Microsoft for $2.5 billion back in 2016. So Minecraft is a pixelized crafting survival game, sandbox game, which means that you will be spawned in a randomly generated world, and then you must collect resources and then build your equipment or shelters or houses in order to prevent from attack by zombies. And then in this world, the world is modeled by pixels. So if you can see from this screenshot, everything is basically a type of blocks. And every block, you can actually transform or move every single blocks and turn them into materials, and so you can create gadgets and then build stuff to it. And the other day, Gojin actually told me that someone in this game actually built a functional computer which can run another instance of Minecraft within the game of Minecraft, which is pretty cool. So why is so in order to solve a problem like Minecraft, which is open, the world is open, and then you probably need to go with a divide and conquer approach where you solve the subproblems first. And then so in Minecraft, many of the tasks can be viewed as skill hierarchies. So which means that, for example, if you try to build a wooden house as shown in the picture, you first need to cut down trees and then pick up the logs and then make those logs into wooden board. And also these skills can be reused. So for example, if you're trying to build a city now, then you will be reusing, if not all, but some of the skills that you learn while building a wooden house. So in order to train an agent that is able to play Minecraft, the agent has to first learn the skill, and then learn a controller that determines when to use and reuse and which skills, and then finally efficiently accumulate more and more skills. So I just provide some background information. So many of the so I'll be quick because some of the stuff were already covered in the course. So if you remember in the last assignment, we had a DQ network, which we had a replay buffer that stores agents' experience in each time step, and then sorry, and then we had two separate networks, one current network and a target network, where it gets updated after every n steps. And then there's also a double DQN, which essentially prevents the over-optimal estimation of the Q function, which instead of doing everything in the current network, we select the action in the current network, but evaluate it in the target network. And then we'll update the Q function accordingly. So a skill here is formally defined as a triple. So I is a subset of states where the skills can be initiated, and then pi, which is a skill policy that I'll talk about later, and then beta is basically a function of state and time, which is the probability distribution of when and skill will stop executing. The author also mentioned a semi-MDP, which produces a skill policy from a 5-tuple, so a set of states, set of skills, the transition probability, which they use a different notation, and this reward is actually the expected discounted reward, discounted sum of reward while the skill is executing, and of course the discounted factor. So a skill policy is basically the mapping between a state and the probability distribution over a set of skills. And so now we have a skill version of the Q function where we replace the action parameter with a skill. So a modified Bellman equation, we have the R, which is essentially the same R here, which is the sum of reward while a skill is executing. And also a skill runs for more than one time step, so we'll need to put an exponent over the discount factor. And distillation is a method that basically trains a student network from a teacher network using supervised learning, where for example, a student network can be trained to predict the output layer of the teacher network. And policy distillation is basically having multiple teacher networks that a student can learn from, and the student network is shared by the teacher network. So I'll introduce the model proposed by the authors, which is called hierarchical deep reinforcement learning network, or the HDRLN. So it's essentially a extension of the deep Q networks that has the ability of reusing skills. So this model outputs either a primitive action, such as moving forward, rotate to a certain direction, pick up, place, or break a block, or a skill. So it has a controller which will take into account the Q value functions or the policies of a certain skill, which was generated by the deep skill module that I'll talk about next. And then it will learn and then try to select which either to output an action or a skill. So if an action is executed, it will execute that action for this time step t. But if a skill is executed, it will execute the policy of that skill until it finishes. And then the policies is generated by the deep skill module. So in a deep skill module, the deep skill module is actually a set of deep skill network. I'm sorry about all the terminologies. So a deep skill network is basically the previously learned skills, and then the DSN will execute. So once a skill is executed, the DSN will execute the policy of that skill. So there are two forms of the deep skill module. A DSN array, which is an array of the deep skill network, or DSNs, where each DSN is a separate network. And a distilled multi-skill network, where it's a common, where it's a single network that represents multiple DSNs. Using policy distillation. So for example, the hidden layer is shared by all the DSNs, and then all the output layer is trained separately using policy distillation. So now we have multiple skills incorporated into a single network, where the authors claim that this can be applied to lifelong learning if we scale up the number of skills. And then here just a combination of the model. So So in this case, in this model, like the parameters, again, we're replacing the action parameter with a skill, and the next state will be a couple steps further because a skill will be executed for k steps, and then this reward is the cumulative reward while the skill is executing. So let's talk about the experiment that they did in the Minecraft. So the state is the raw pixels from the picture frames in the game, and then they've set the primitive actions as move forward, rotate left and right for 30 degrees, break, pick up, or place an object, and they give a small negative reward at every time step. And then a non-negative reward after completing each task. And they have three domains where they train the agent, a subdomain where they train the agent with each skill individually, a two-room domain which has 2 rooms, and a complex domain that has 3 different rooms with 3 different tasks. And then they've set different time steps for each episode for each domain. And then for the subdomain, the agent was initialized at a random position, and with multiple rooms, the agent was initialized in the first room. So this is the first subdomain where in each scenario they will train one single skill. So this one is navigating. In this one, the agent was supposed to navigate to where the goal is, and then this is also a navigation skill, but with obstacles. And this is a pickup domain where the agent must pick up the goal object. And then here is the placement domain where the agent is supposed to place the object at the target position. And this also accounts for the break domain because all it has to do is executing a different primitive action. So some of the challenges are in the trainings are the identical walls, which pose a visual ambiguity, and also obviously the obstacles, and then navigating to a specific location, and then doing a specific action. So the authors trained the agent using a vanilla DQN, and then they optimized the parameters on a Minecraft emulator where they set higher learning ratio and higher learning rate, less exploration, and a smaller experience replay. The authors didn't really get into much detail, but they didn't mention of why they're doing this, but they did mention that it has something to do with the frame rate in a Minecraft. And then, so while the subdomain training is kind of trivial, so the agent was able to have a success rate of almost 100%. And then the more difficult domain, the first is the two-room domain, where the agent appears in the first room, and the agent is supposed to navigate to the exit and enters the second room, where it's the room where they had the first navigation task. And then in the room 1, the exit is actually different from what the agent was trained in the previous subdomain. So this time the agent was trained with the previously learned skill, or DSN, in the two-room domain by reusing the skill. It had so after the first epoch, the HDRLN solved the task and had a higher rating with the baseline DQN, and then after 39 epochs, it had a success rate of 76%, and while DQN has only 50%. And then the reason for that was, again, wall ambiguity. So in DQN, the agent might get stuck because all the walls look the same. Also, the author tried something interesting. So they used they used the DSN that was trained previously directly into the two-room domain without additional training. And then it also succeeded and also had a higher reward than the DQN, although it's lower. So as you can see from the result chart, so this is using DQN. This is using the previous trained skill without actually without additional training for the new domain. And then these are the using the previously trained DSN, but also trained for the two-room domain. So this is after the first epoch, and this is after the last epoch. Oh, and then and now the deep skill module was also added in into the training, and then it was applied to the more complex domain. Where let's go back. Where now we have 3 different rooms. So in the first room, the agent is supposed to navigate through obstacles and then find the exit. In the second room, it's supposed to pick up an object and then break the door and then enter the third room where it must place the object at a specific position. So NAA incorporated the other 4 previously learned skills, or DSNs. So pick up, navigating through objects, break or place. So for the DSN array form, so these 4 DSNs just form a simple array. And in the multi-skill, the distilled multi-skill network, these skills will form a teacher network, which will distill to a single student network. And then the model will also learn a control where it will switch between the different skills that was learned previously. So again, here's the result of the success rate. So here, yellow, we have, oh, actually, sorry. In this model, they were using double DQN to train the agent. So by using double DQN only, the agent was not able to complete any of the tasks. And then the blue curves are using the previous previous DSNs only, I believe. They didn't do a good job marking this. Right. So they were using the previous DSNs only, and then using DSN array, and this was using DSN array with the training of double DQN, and this was using the distilled multi-skill network with the double DQN, which resulted the highest success rate. And if you notice, when double DQNs used, the variance was actually lower. The authors also measured the usage of the skill. So here it shows the probability of when the agent's using a skill. Here is called options, which is just another word for skill. So if you notice, after about 50 epochs, the agent started using the skill, and then the skill learned previously, and the rewards start to going up. And then after about 90 epochs, the agent was reducing the use of skill because it was trying to utilize the primitive actions, because some of the skills might be suboptimal, so there's no point of exploiting that skills. And then so basically the skills must be refined with primitive action. And also in the case that when the skill is the policy of the skill is really bad, you can just execute the primitive actions. Oh, I'm going kind of fast. So just to conclude, so in this paper, the author gave a extension of DQN or double DQN in the Minecraft domain, which incorporated the use of previously trained skills into their model called the HDRLN. And while multiple skills are incorporated into this deep skill module, which has a form of either a DSN array or a distilled multi-skill network. And then in the end, it generated a better performance than the DQN or the double DQN. So the contribution of the paper, where the claim was they had laid the foundation for the building blocks of lifelong learning, which again, which needs efficient knowledge retention and efficient selective transfer of knowledge and skills, and then the effective and efficient interaction between the two, and also provide evidence of a potential knowledge transfer without additional learning. So some of the future works. We're involved capture the implicit hierarchical structure while training the skills, and also learn and refine the skills online. And then finally, try to train the agent in the real-world Minecraft scenarios. And then that concludes my presentation, and thank you for listening.